Hello, and welcome back to Greg Does Physics. My name is Greg, and today we're going to be doing some physics. Specifically, what we're going to be doing is problem 2.36 in Griffiths E&M, which asks us to consider two concentric spherical shells of radii A and B. Suppose the inner one carries a charge Q, and the outer one a charge negative Q, both of them uniformly distributed over the surface. Calculate the energy of this configuration, A using equation 45, which I've written here, and then B using equation 47, and the result of example 9. So wanting to calculate the energy that's stored in this charge configuration, we have this equation, epsilon naught over 2, the integral of E squared, E being the electric field's magnitude, d tau, so the volume integral. So our job then is to find the electric field equation for this configuration so that we can integrate over all space. Now, there are a couple ways that you can calculate the electric field, and that's an important thing to keep track of as you go through chapter 2 of Griffiths, is this idea that there are different ways to calculate different quantities, be it the electric field, the potential, the or whatever it is, and based on what quantities you have available to you, the electric field, the charge distribution, the potential, whatever, that gives you the license to go back and forth between those. And when you come into a problem, you should assess what you're trying to find, what you have at your disposal, and then over the course of chapter 2, Griffiths will give you a bunch of different equations, different things to put in your sort of toolkit, like, for example, Coulomb's law, Gauss's law, the divergence and the curl of the electric field, stuff like that. And then you can use that stuff to motivate a easy to do solution for whatever it is you're trying to find. And in the case of this, what we want to find is the electric field. And we have the charge distributions distributed over these concentric spheres. And we could calculate it directly using Coulomb's law, but if you've watched my video on 2.7, then you know that that is a huge pain to do. And we want to try and make this as easy as possible for us. Another way to calculate the electric field in cases of symmetry, such as this case where each charge distribution has spherical symmetry, then what we can use is called Gauss's law. And Gauss's law looks like this. It's the closed loop integral, the electric field dotted with dA, and we say that it's equal to 1 over epsilon naught times the charge enclosed within that charge distribution. And so if we were to create a Gaussian surface, that's the surface that we're integrating over. We have the license to choose whatever Gaussian surface we want, but naturally we're going to want to choose a surface that has some symmetry with the electric field so that we can take the electric field out of the integral. In this case, with these spherical distributions, it would be a good idea to have a Gaussian surface of a sphere. And so we could, for example, put a Gaussian surface of a sphere that's inside both of them. But of course, inside this sphere, there's going to be no charge enclosed, since the charge is on the shells of these two spheres. And so in that case, our electric field, of course, would be 0. Likewise, if we were to draw a Gaussian surface outside this whole thing, our charge enclosed within that Gaussian surface would be Q, which is distributed over our inner shell, minus Q, which is distributed over the outer shell. And so that, of course, plus Q minus Q adds up to 0. So again, there would be no charge enclosed, no net charge enclosed, if you create a Gaussian surface outside of both shells. So the only time when we're going to have an enclosed charge is when we draw our Gaussian surface in between the two shells. And so that's what we'll say. So Our dA in spherical coordinates, if our dA is for the surface of a sphere, it's r squared sine theta d theta d phi r hat. And so, since we expect our electric field outside of this inner shell to point radially outward in all directions, since it's a positive Q, evenly distributed over the shell, then we can take this out and we can say the magnitude of E, and then whatever R we choose for our Gaussian surface. Pull the R squared out of the integral, and then the R hats, since E is in the R hat direction, they're dotted. Sine theta d theta d phi, which by now you should know that integrating theta, the polar angle from 0 to pi, phi, the azimuthal angle from 0 to 2 pi, this is 4 pi. And this is going to be equal to positive Q over epsilon naught, which tells us that our electric field is going to be 1 over 4 pi epsilon naught Q over R squared, and it will be pointing radially outward. And you notice that this looks a lot like Coulomb's law. And it kind of looks like we're almost looking at this sphere of shell, almost like it's a point particle, which is placed at the center of the sphere and has a charge of the net charge that's placed on the shell. So that's our electric field. And so then, looking at this integral for our work, we want to take the magnitude squared of that and then integrate over all space. So epsilon naught over 2, and then we can take out our constants as well. So Q squared over 16 pi squared epsilon naught squared. So then we could actually just wrap that, and in fact we could just write this as 32. So Q squared over 32 pi squared epsilon naught integral of 1 over r squared, and our volume element for spherical coordinates is r squared sine theta dr d theta d phi. And oh, sorry, this should be 1 over r to the 4th, since again it's squared. And so then, again, knowing that our d theta d phi terms will just integrate to 4 pi, we can write this as Q squared over 8 pi epsilon naught integral of from A to B 1 over r squared, because as we recall, this equation for the electric field is only valid for A is less than R is less than B, and the electric field is 0 elsewhere. So 0 for R is less than A, or 0 for R is greater than B. And so this integral, of course the antiderivative of 1 over r squared would just be -1 over r to -1 over r. So then we could just bring the negative out to switch the limits of integration, and we'd have 1 over A minus 1 over B. So that's our work. But that's from part A. And part B wants us to use equation 47 and the results of example 9. Equation 47 is this. It is saying that the work total is equal to W1 plus W2 plus epsilon naught E1 dotted with E2 d tau. And where is this equation coming from? It's just saying that if we have two if we calculate the work of two separate charge distributions, so for example, we calculate the work of the inner sphere and we calculate the work of the outer sphere, work does not obey the principle of superposition, unlike, say, the electric field or the electric potential. And so as a result, we pick up this cross term. And so if we want to calculate the total work, using just the individual contributions to the work from each sphere, then we also have to calculate what this cross term is going to be as well. And then it also asks us to use the results of example 9. The results of example 9 being that, where's example 9? Example 9 just is the equation for the work for the energy of a uniformly charged spherical shell of total charge Q and radius R, and it says for such a distribution, our work would be 1 over 8 pi epsilon naught Q squared over R. And so then our work 1 would be Q squared over 8 pi epsilon naught A. Then our W2, the work of the energy of the outer spherical shell, would again be, it would be negative Q times negative Q, so still Q squared over 8 pi epsilon naught B. And then we have this cross term. And so the electric field of E1 and E2. But let's recall, the electric field of both of them for R is less than A is 0. The electric field of the outer shell for R is less than B is 0. And so when we dot those two for R is less than B, we're going to get either 0 times something or 0 times 0, and so it'll just be 0. So the only time when these two dot together and give us a non-negative value is when our R is going to be greater than the radius B. Likewise, we can look at this equation and it's still going to hold up. And so dotting the two together, the inner sphere would have positive Q, the outer shell would have minus Q, and so this would look like so minus Q times Q over 16 pi squared epsilon naught squared, which we can just cancel with this one outside here, and then integrated from and then it's 1 over r squared times 1 over r squared, which of course is 1 over r to the 4th. And then again, our volume element in spherical coordinates is r squared sine theta dr d theta d phi. Okay, great. So then we can bring out Q squared over 8 pi epsilon naught 1 over A plus 1 over B. And then over here, again, our d theta terms, that is going to go to 4 pi as always, so we can bring the 4 pi out. So minus Q squared over 4 pi epsilon naught, and then from B to infinity, dr over r squared. There's going to be Q squared over 8 pi epsilon naught 1 over A plus 1 over B minus Q squared over 4 pi epsilon naught. And it would be, again, the antiderivative of this is negative 1 over r, and so 1 over infinity just approaches 0, and so then it would be negative, 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 if we do that, we can do that 1 over b. But then we can see that we can get these outer terms to be the same if we just distribute a 2 into here and then turn this into 8 pi epsilon naught. And so then this would be basically 1 over b minus 2 over b, which is going to give us negative 1 over b. And so then this will become q squared over 8 pi epsilon naught over A minus 1 over B, and they're the same. So there we go. So again, this problem isn't, I wouldn't say it's extremely complicated, but it's a good test of remembering, okay, what is the best way to calculate the electric field? Just remembering that Gauss's law can make our lives a whole lot easier when we have charge symmetries like this. And that there are different ways to calculate the energy of a given charge distribution as well. And so we can do one that is sort of adjacent to superposition, except since these energy doesn't follow the principle of superposition, we pick up the cross term, or we can just do it directly with this equation. Regardless, they give us the same result. And that is all for this episode, so thank you.